So in this second tutorial, we'll keep working with relatively simple models. So we have this horizontal truss structure. Okay, so we have a total length of 30 inches for the truss. It is discretized into a total of 3 equally sized truss elements. And then the rightmost node is subjected to a cyclic horizontal displacement history. The leftmost node is fully fixed, let's call it, against any translation, and then all the remaining nodes are allowed to fully translate horizontally. We also are given various quantities of interest here. The cross-sectional area is 1 square inch. We have elastoplastic material with an elastic modulus of 29,000 ksi, a Poisson's ratio of 0.3, a yield stress of 50 ksi, and a linear hardening modulus of 290 KSI. So without further ado, let us begin creating this model. So once again, I'm opening the FEMultiPhys builder. I'm going to model and then model editor to open our model editor graphical user interface. And this time, contrary to what I did in the first tutorial, I'm going to input the coordinates of the nodal points and the element connectivity information through the table capabilities. Let us begin by first defining the materials and sections, although it's not necessary. You could easily, let's do it actually. Let's define the nodal coordinates first of all. So we go to mesh node table editor. So our first node with ID 1 is at location x, y, and z or equal to 0. Then let's click this add row button to add the second node with ID 2. It is located at the location x equals 10 inches, y equals 0, z equals 0. Then we add yet another row. This is node 3, which is at x equals 20, y and z both equal to 0. And we add the fourth and final row, which gives us the coordinates of the fourth node, the rightmost node in our mesh. X equals 30 inches, y equals 0, z equals 0. So we can click on apply nodes and we should be able to see our nodes here. I have my node radius set to 1. I can change it to 0.1 and have these tiny nodes appear on my viewport. Now let us also define the element information. So I go to mesh, element table editor, I click on it, and we will obviously have the same section assignment to all the elements. This will be the first and only section we will define. So what we have to define for each element is the ID number of the element. So 1 for element 1, 2 for the second element, and so on and so forth. The section ID, which section law we are assigning to each element. All our elements in this case will be using section ID law 1, and then the connectivity, the nodal connectivity for the elements. So for our first element, we will select nodes 1 and 2 as the two nodal points. Okay, then we can click on add row, go to ID equal to 2, the second element that we defined. Section ID again is 1, and the two endpoints are nodes 2 and 3. And then we add the third and final row for the element table editor information, where the third element in our mesh uses also the section with ID 1, and its end nodal points are nodes 3 and 4. And we can click on apply elements and we should be able to see our mesh. Once again, we can see the nodal labels if we so choose. We can activate to see the element labels if we so choose, and so on and so forth. Now, let us continue by defining the materials and defining the information for our section. So although we were able to define elements using the section with ID 1, we have to ensure that we have defined all the properties of that section with ID 1 before we export our model. So to define our material laws, we go to materials, then add edit material. And what I'm going to do is, for defining the first material, I'm going to give a name which is informative. I'm going to call it elastoplastic linear hardening. And I'm going to select the material type to be this steel 01. It says uniaxial steel, so it's basically an elastoplastic material or relatively simple one, similar to the steel 01 material of OpenSys for those of us who may have familiarity with OpenSys. And again, the general idea is it's quite informative what we need to define. We have to give the elastic modulus, which again here is equal to 29,000 KSI, so we can keep this preset here. The yield strength is 50 KSI, again we can leave it to the preset here. The hardening modulus, the linear hardening modulus is 290 KSI, so I set this value here. And then for hardening, we have this integer parameter ihard. A value of 1 means we use isotropic hardening, a value of 2 means we have kinematic hardening, and I'll prefer to use kinematic hardening because it's better tailored for what we will be having as cyclic loading scenarios. And then the Poisson's ratio, as we already mentioned, is equal to 0.3. Poisson's ratio doesn't matter for truss elements. It has some meaning for cases that we use this steel 01 material in elements like continuum-based beam elements, for example. Okay, so I'm going to leave this material here. I'm going to click on Add and Update, so we should be able to see this material being defined in our model tree. Okay, and I'm going to just define another material, which I will use actually just to check it at the end, towards the end of this tutorial. So I'm going to define a second material law. But this time, just to get a bit fancier, we are going to use this AF plus material law, which is again a uniaxial material law with nonlinear hardening. The AF initial stand for Armstrong-Frederick, so among other things, it includes the Armstrong-Frederick law, which is a law allowing us to model what we call nonlinear kinematic hardening, so we see curved shapes in our hysteretic loops. That's the idea. So again, it's pretty self-explanatory what we have to give. So we have 29,000 KSI for the elastic modulus, 0.3 for Poisson's ratio. The initial yield stress is 50 KSI. Then we have to give, parameters that control isotropic and kinematic hardening. For this age iso parameter, I'll set it equal to 0. I don't want to have any isotropic hardening in this case. This beta parameter also is related to how the isotropic hardening modulus varies. And then we have these two parameters, Skin1 and Gamma1, that control what we call the first component of back stress. We also have Skin2 and Gamma2 controlling a second component of back stress. For this example here, we'll just maintain a single component of back stress. So we are going to give a value, let's say, of Skin1 equal to 800. This has units of KSI. A value of Gamma1 equal to 50. This kinematic one means what is the initial slope of the, to a large extent, not exactly, but very close to the initial slope of the post-yielding stress-strain curve that we will obtain. This Gamma1 basically controls what we call the saturation of hardening. That is how quickly the hardening curve tends to become a flat curve, so that our yield strength of the material ceases further increasing with further accumulation of plastic deformations. So I'm going to call this material, let's call it nonlinear hardening, and click on Add Update. So we have our two materials. Let's proceed with defining our section. So we go to Sections, Add Edit Section. Section ID, we leave it to 1. The type is Truss, and we can give our name. So let's call it, let's make it a bit meta. So we'll just call it Section 1. Okay, we have the material ID. We can select whichever of the two material laws we define. For the time being, we'll keep the elastoplastic with linear hardening. The sectional area, again, it's 1 square inch, so we leave it equal to 1. And this optional feature, sec shape, that's a neat feature. It has to do with how the shape of the section of the truss elements will be plotted for post-processing. So you have various options here. I'm going to use circular sec shape just to showcase this capability. So I'm going to click on Add and Update, and I should be able to see this first section created in my model tree. Okay, so now if we go back to our mesh definitions, for instance, if we go to this button here that allows us to edit our elements, Since all our elements have already been assigned the section I with ID equal to 1, we know that the section that we have defined will actually be assigned to all these elements. Let me change my view here to a top since this is a 2D model. I'll leave the dimension space to 3D, so this means all our nodal points are by default taken to have a triad, a triplet of coordinates x, y, z, and also a triplet of nodal degrees of freedom, nodal displacements. So what I'm going to do next is apply the fixities. Okay, so if I activate the nodal labels, we know this leftmost node, node 1, must have all 3 of its translations fully fixed, and all the remaining nodes 2 through 4 must have the vertical translation, actually translations in the y and z directions fixed. We also have to fix the z translation, otherwise we have a mechanism in the 3D context. So what I'm going to do to define the fixities, I go to the boundary conditions, find the fixed restraints option. Okay, we leave the name as BC1, and then we leave checked all 3 translational mechanical degrees of freedom. Then we can give the nodal ID of 1 if we want, or we can click this button, pick from mesh. We can click on node 1 so that we see the node IDs is populated as 1. And we can click then, we are done with this first boundary condition, we can click on apply and add another. We see the symbols of fixity drawn for node 1. We now go to the remaining nodes. So actually I'll try to move this dialog. Okay, it's a bit, how should I say, idiosyncratic, if I can use the term. So again, we already have activated the click to pick option, let's say, the clicking and picking option from our window. So all we have to do is individually click to nodes 2, 3, and then 4. Okay, and make sure that we uncheck the U1 degree of freedom so that these nodes are allowed, let's say, to freely translate in the X direction. So I can click then on apply and close. And lo and behold, we have our fixities defined. Now, because I want to apply a cyclic displacement history on node 4, okay, what I'm going to do is basically first define a curve which will give me a function of time, so that later on when I apply the prescribed displacement boundary condition for the horizontal displacement of node 4, we can say this displacement varies in time in accordance with this particular curve ID that we have defined. So to define a curve, surprise, surprise, we have to go to the define menu, find the curves option. You see there is a pre-populated curve, let's call it template, but we don't, this is not the curve that we need to have. So we can click, first of all, let's give a name, let's call it cyclic history. And then we have this quick template that allows us to define some simple cases. I'm going to get fancy here, so we can delete these points. Okay, we have point 0, 0. This means at time 0, our curve has a value of 0. Then I press enter in my keyboard, and let's add some additional points. Let us think actually, what points would we like to add? Let's say that at time 1, so at time 1, we have a displacement of 1. Okay, you see automatically the curve is interactively drawn for our viewing pleasure, if I can use the term. Then let's add an extra point, which is, okay, at time 3, we have a displacement of -1, right? Then let's say that at time 8, we push up to a displacement of 4. And then we can even have an extra point at time 10, we still have a constant displacement of 4. So basically you can see this interactive drawing of the curve. You can even click this neat preview button and see how this curve definition will actually look in the txt input file once we create it. That's all we need for the time being. We can click on add update. And we should be able to see the curve under the curves heading here, our cyclic history. And we can also click on this edit button to edit it if we want. We can even delete it. That's not what we want here. All that remains for us in the model setup is to prescribe the displacement in the horizontal degree of freedom of this node 4. So what I'm going to do is go to, I think it is in boundary conditions, yes, and we find prescribed displacement. Okay, let's leave the name as displacement 1, or let's give something fancier, cyclic displacement. The degree of freedom, we leave it to 1, so 1 means the X translation. Here, the first degree of freedom. We have a reference value and a curve ID. What this reference value means is this is a number that will multiply the curve ID if we want to have a curve, okay? We can have a curve ID of 0 if, we don't want to have a dependence on time. So we will leave the reference value to 1. So if we had the reference value of 2, what this would mean is that at its time value of our analysis process, given the time, we would go to this curve with ID 1, find the value of the curve, then multiply it by a value of 2. This would be the displacement that we would be applying. Right now, we just want to apply the values of curve 1 unaltered. That's why we leave this reference value, this multiplier, if you prefer, if you will, of this curve equal to 1. Okay? We will apply it to given nodes, and once again, we will click the pick from mesh option here, and then click on node 4 to select it. And once again, we can go to preview and see all these options that I have here. We can click then on apply and close, and everything should be ready to define the model. So to conduct my analysis, I'm going to go to the solver menu to define the various options of the analysis. Before I do that, let's select the post-processor once again to be FEMultiPhys editor. Okay, we could have opted to use any other post-processor, but let's simply rely on the editor once again. So let's go to the solver options now, find these solver settings. The analysis type will once again be static, an implicit incremental iterative procedure based on Newton-Raphson iteration. Let's leave the iteration scheme to full Newton-Raphson. Let's leave the time step equal to 0.01, and then let's make our termination time here equal to 8.0. So we try to run the entire cyclic displacement history that we defined. We also have optional features here, like what is the minimum time step that we want to allow, what is the maximum time step, what is the time step with which we want to print output. If you leave this blank, they are automatically set by default equal to the time step value that we define here. Let's leave the maximum number of iterations to 100, and let's leave the tolerance to 0.005, 0.5%. What I always like to do is also use this option here, this relative option. What this means is that the convergence is checked based on a relative residual norm. So we find what is the internal force norm, the magnitude of the resistance vector of our structure at any time, and then the violation of equilibrium force vector must have a magnitude that doesn't exceed this number times the magnitude of our internal force vector. So that's the meaning of a relative convergence criterion. We are not going to use any of the fancier capabilities like dynamic relaxation or whatever. So I think we should be able to proceed with all that. Let me scroll down with my mouse, go to preview. These are the options that we should be having here, and I'm going to click on save settings. And now we should be able to export our analysis and run it. So I'm going to go to run, export to txt. Okay, I'm going to call this model 1D bar, let's say, and then I'm going to click on export download. I'm going to my local drive where I have my FEMultiPhys analysis. I have lots of them, as you may be imagining. I'm going to create a new folder which I'm going to call 1D bar. And then inside this folder, we have once again the 1dbar.txt file, which we can save. And then we should be done with everything that we had to do here. We now should be able to run the analysis. To this end, I'm going to bring forth the FEMultiPhys builder form, go to analysis, then run analysis. look for the folder that I created in my computer. It's in FEMultiPhys folder and then the subfolder 1D bar. I find the 1D bar.txt file, click on open, and I should be able to see the analysis running over here. So let us try to now post-process the results. Let me try once again to see if we are luckier and we won't encounter any glitch. So we go to File, New Model, and then I go to Post-Process Load Results. I'm already in the folder that I was looking for. I find the output subfolder, 1dbar.mpm file, click on Open, and I should be able to see an isometric view of my model. Again, with my mouse wheel, I can interactively zoom in or zoom out. And here is the other neat feature. If you click on this 3D button here, you should be able to see. And then, if I left click and hold down the left click button and move my mouse, I should be able to rotate my view manually. You can see these truss elements having indeed a circular cross section. We can also animate the results. So if we go to post-process and find animate steps, the mode here, we can make it loop or bounce or once. I'll leave it to once. Let's put 20 frames per second. So I click on play and you should be able to see this animation here. It's a bit slow, so let me stop, make it perhaps 60. By the way, this is sometimes very slow when you try to load very heavy models, but now it should be quite fast. So we can see the, basically the progression of the movement. This should be node 4, by the way, which is moving back and forth in the X direction. I can even go to a top view, move this a bit out of the way, and I should be able to see again this animation. You can also see various other results that might matter. For instance, let me close this window. You can go once again to find the contour plot. For instance, the quantity you can select U sub x so that you see a contour plot of the nodal displacement. At time equal to 0, we indeed have a maximum displacement of 4 at the rightmost node, which is node 4. Again, you can go to post-process, toggle node labels and see node 4 here. Let me turn this off. You can also see other quantities. For instance, you can see the axial strain for the element. So I think, yeah, it should be in element axial strain. I don't see it anywhere, to be honest. Oh, there it is, axial strain. So this is an axial strain plot for our elements. You can even see, I think, a plastic strain. Yes, so this is the plastic strain for these elements. So again, this is the general idea. You can play with various options. We can also create a force displacement plot and save it. To do that, we go to post-process, go to XY plot. And what I'm going to do as source for the x-axis, I'm going to select a nodal quantity. We can go to displacements x, it's the x displacements we want. And you can either give the node ID as node 4, or you should be able to click on the window and select this is the time, the history of displacement at node 4. But for the y-axis, what we want to do is again keep it as nodal quantity, keep the node ID to the pre-selected 4, but now I'm going to select reactions x. So this is the x external force that we must apply to control the displacement of that node, and we should be able to see this hysteretic force displacement plot, okay, which basically has a shape that looks like an elastoplastic hysteretic loop with constant linear kinematic hardening, right? For those of us who may be knowledgeable about this kind of stuff. You can even save this hysteretic plot by going into this icon here, left click on it, and you should be able to save something like, let's call it force vs disp. Let's call it something like this. Actually, let's put it in the main directory here, click on save, and I'm going to find this folder on my computer. Let me bring it here from my other screen. I'm going to oh no, I'm sorry, shouldn't open the input. I should open the force versus disp plot, and I should be able to see, right? I mean, this is the information which I can then copy and paste in other apps like Excel, or even, pass it to, let's say, a Python-based script that can generate neat plots, or a MATLAB script, or whatever. So before completing this tutorial, I'm going to, let's say, get a bit fancier. So I'm going to bring back my input file. So I'm going to file new model, so I forget about everything. I can go to import txt, find the 1dbar.txt file in my folder, and then open it. Once again, we can go to the mesh view if we want to see our mesh. But what matters the most is I'm going to change the material that I have assigned to my section 1. So to this end, what I'm going to do is go back to sections. Actually, we can go to sections and find edit section. The trouble is, if you go there by default, you populate a new section window, and you have to go make this one, and be careful not to overwrite something, so it gets tricky. I would always advise you go to the model tree and find section 1, find the edit button here, and all I'm going to do is change the material ID assignment from material 1 to material 2, the one with the nonlinear hardening, and click on add or update. Okay, you can verify if you go back to your section, it should now be having material 2 assigned to it. And all I'm going to do once again is go to run, export txt. And now I'm just going to overwrite my previously created txt file. So I leave this in the name 1dbar, click on save. I should get this prompt and click on yes, I want to overwrite my previous file. And what I'm going to do is rerun the analysis once again. So analysis, run analysis, and then we select the 1dbar, run it. Okay, so what we can do then once again is go to File, New Model, and find post-process, load results, output, select 1dbar.npm, and open it. And again, the only aspect I want to showcase, we can again post-process everything we saw already, but I want to see how the load versus displacement plot for node 4 has changed now that we use the nonlinear kinematic hardening model. So to do this, we go back to post-process XY plot. The x-axis we keep nodal quantity, and now we have to keep node 4 x displacement. So this is the x displacement plot for node 4. Okay, and then we go for y-axis. We leave node 4, and the quantity that we will select for this is x reactions. And lo and behold, you should be able to see this curved hysteretic plot. This is the impact of using a material model with nonlinear hardening, nonlinear kinematic hardening in this particular case. And you may also notice this flattening behavior, which again has to do with this saturation behavior inherent in an Armstrong-Frederick model. Feel free to experiment with that. For instance, if you can save this, by the way, once again. I'm going to just showcase something else. Go to File, New Model, and then once again go to the recent model list and import the 1dbar. All I want to show is if you try to edit the nonlinear hardening model, you could experiment changing this value of gamma 1. You should be able to verify that the larger the value of gamma 1, the faster you end up with a flat curve, when you keep increasing the deformations. If you use a low value of gamma 1, you may see that even for the largest displacements that I applied there, my stress strain plot never acquired a flat slope, let's say. And of course, feel free to experiment with other uniaxial materials if you so wish. So you can see there are various options, lots of them. You can use, a generic hysteretic material. You can use material models for reinforcing steel. this is the one that I would definitely advise. It's the most refined one, the steel DR. That's a uniaxial reinforcing steel material. You can use a Menegoto Pinto uniaxial steel material and whatever. But for the time being, this pretty much concludes this second tutorial, where hopefully it allowed us to get a first understanding of how we can conduct a nonlinear static analysis and how various material definitions can actually affect our results. So thank you for your attention, and I'll be seeing you soon in one of our subsequent tutorial sessions.